Okay, here's this fun little applet. You can find it online. Just search for Newton's canon. But in any case, it shows an example of what happens if we scale up the shooting of an object in the horizontal direction. So we've got a cannon on top of the mountain. I think you can see my cursor. We've got a cannon on top of the mountain. We're going to shoot horizontally. We can change the speed at which we shoot by dragging this thing over here. So it's going to shoot horizontally, but gravity will pull it down. So it'll travel in parabolic motion towards the ground. But it's not going to look quite parabolic to somebody on the ground because the ground curves. So anyway, let's just see what happens. Sound effects are on too. Okay, so, well, that looks sort of parabolic, but okay. So let's go ahead and increase the initial speed a little bit. Let's just increase it a little bit. Let's go to 3400. Okay, you can see, right? So there's your parabolic motion. It goes out a little further. We can increase it further, but notice that the more we increase it, now the Earth's surface is curving away from the motion. So the object is actually going to fall farther than it would if it was a flat Earth. So go ahead and fire. Boom. Okay, not fast enough to make much of a difference. Fire. Oh, boom. Oh, look at that. I actually I did increase that more than I meant to. Let's do something in between. Boom. So you can see all of the, I don't know why the sound when it lands is different. Oh, it lands in the water. I see. Initially, let's listen to that. Yeah, it landed in the water as opposed to boom, landing on the ground or on somebody's head. Okay. So this is kind of cool, right? So look what happens. Look at if you imagine a flat ground, all these look parabolic, but look at what it looks like relative to the curved surface of the Earth. It's actually looking kind of circular, right? It looks kind of circular. Let's go ahead and increase the velocity a little more. Okay, I think whoops, that was less than last time. It's in the water. Boom. All right, a little farther. Ooh, water. I don't know if it's. And notice that we're actually able to shoot and have it land. Ooh, ooh. Oh, look what happened.
Ow!
Ooh. I hit myself in the head. So what happened is it was falling, right? The whole reason why it travels in these red trajectories is because it's falling towards the Earth. And it's actually falling because the gravity points towards the center of the Earth. It's falling towards the center of the Earth. But the Earth's round. So if you shoot it fast enough, it's going to miss and it's going to go all the way around. And what do we call that when something goes all the way around? It's called an orbit. So what it means for something to be in orbit, what does that mean? It literally means it is falling towards the center, but it has a large enough tangential initial velocity so that it misses and it never hits and it always goes around. Let's go ahead and increase the speed a little more. Fire. And it's falling, but the Earth isn't there. It's falling, the Earth isn't there. So it's just going to keep on going around. And
Ow!
ow, right? And if it didn't hit me, what would it do? It would just keep going around and around and around, and that's what it means for something to be in orbit. The reason why the moon orbits around the Earth is because the moon is falling towards the center of Earth. But somebody gave the moon a fast enough tangential velocity relative to the Earth's surface so that the moon always misses. It's absolutely true, 100% true. It is actually falling towards the center of Earth, but it doesn't get closer to the Earth because the Earth is round. It's always falling, but it's got a fast enough velocity. It's in outer space. It doesn't slow down. There is no friction. And who gave it the push? It was the Big Bang, right? The Big Bang gave it the push. Or if you are a religious person, you can say that God gave it the push, but it was the Big Bang that gave it the push. Same thing with the Earth around the sun. The Earth, it just got the right tangential velocity around the sun, as did all the planets in our solar system, so that they go around without hitting. And sure, they're not necessarily circular motion. This can also be right. It can be elliptical motion, but it's you got to give something fast enough. Now, what happens if you give it too fast a tangential velocity? Maybe you can guess what will happen if I give it too fast a tangential velocity, right? If I shoot it too fast in the tangential direction, what's going to happen? Oh, it doesn't allow me to increase the speed enough, I don't think. Let's see, does it come back? Yeah, it comes back. Okay, so it turns out that if you shoot it too fast in the tangential direction, it's going to leave the Earth's orbit and it'll go somewhere else. So in order for a planet to be stuck in a star's orbit, in order for a moon to be stuck in a planet's orbit, it had to be given the right velocity, and there's a range of velocities, you can see it here. It had to be given the right velocity in order to be trapped in that orbit. And if it's too fast a velocity, it leaves the orbit, and it's too slow a velocity, it bangs into the object. Just the right range of velocities, and it's in orbit. So the last thing I want to talk about is, what is the acceleration of somebody who's in orbit? They're undergoing centripetal acceleration. Let's just pretend it could be elliptical, but so we can approximate. Most orbits are well approximated by being circular orbits. The acceleration is centripetal, right? It's the acceleration that they're falling towards the thing that they're orbiting. And in the case of the moon, what's the moon's acceleration towards the center of the Earth? Well, actually, that's a bad example. Sorry. Let's take the space station. Space station is an orbit. Any satellite that we have is an orbit around the Earth. What's its acceleration? The acceleration is 9.8 meters per second squared. Because it's falling, that's why it's in orbit. If there was no gravity, it wouldn't be in orbit. It wouldn't be going around the Earth. Now you might say, but wait, isn't the acceleration in outer space smaller than 9.8 meters per second squared? Only a little smaller. The space station's only like 100 miles up. It's only a little smaller than 9.8 meters per second squared. We can figure it out when we get to that chapter, but maybe 9.6, I don't know, 9.7, 9.5 meters per second squared. So there is a gravitational acceleration in outer space. It is a myth that there is no, right? People think, oh, you're weightless, you're floating, there is no gravity. There is gravity, that's why you're in orbit. But you're falling at the acceleration due to gravity. This is an important point, right? You're falling at the acceleration due to gravity. There is no earth underneath your feet to stop you from falling. So that's what makes you feel weightless, because there's no floor to hit. But you're still falling towards the center of the Earth. You're still accelerating, which is why, to some extent, astronauts get queasy because of those accelerations. What does it mean to be weightless? What does it mean to be weightless? It means you are accelerating at the acceleration due to gravity. It doesn't mean you're not accelerating at all. And we'll talk about this more in the forces chapter. But if you jump off the top of a building, you're weightless. You're weightless until you hit the ground, right? If you're on a trampoline, you jump up, you're weightless until you hit the trampoline again. That's what it means to be weightless, is you're simply falling at the acceleration due to gravity. Okay. Moving along. Have a wonderful day.